Okay, so one of the cool things in electrochemistry is you kind of take what you learn about redox reactions and then you apply it to some real solutions chemistry. When we talk redox reactions, we're not really thinking about anything that's happening to the sides of things. And when we're balancing chemical equations then and balancing half reactions, we have to take into account what happens when they're in different environments, because these things don't usually just happen in water. If we think about something like batteries, for example. We think about battery acid. Well, there's a redox chemistry process that's occurring in an acidic environment. So what the heck is actually going on? How do we think about the half reactions in that context? So I want to talk a little bit about the steps, and then we're going to just get into the details of actually applying them to chemical systems. So here's the steps. We're going to first, like we've done with redox kind of processes before, assign oxidation numbers and identify which is being oxidized, which is being reduced, and then which one is the reducing agent, which one is the oxidizing agent. So we have a sense of what's going on kind of from a redox perspective. Then we're going to show the half reactions. And when we balance these half reactions now, we have to take into account more than just the number of electrons that are being gained and lost. When you, at an introductory level, learn about redox, then it's really all about how many electrons are being gained in the oxidation step, how many electrons are being lost in the reduction step. But realistically, there's some chemistry that's occurring with the water, with the acidic environment around it, with a basic environment, which we'll get into in a different video. And then how do we balance out all the charges of these things when there's more than just an ion on one side and something neutral on the other, which is usually kind of our go-to example, is the formation of ions is in a redox process. So it's more complicated than that. So we're going to get into that step, and then you combine everything and simplify it down. So we're going to keep these steps in mind, and I'll refer back to them throughout the video. But for right now, let's look at an actual example. So if we go back to step 1, and we think about this particular reaction, then step 1 is to assign all the oxidation numbers and to identify what is being oxidized and what is being reduced. So let's assign oxidation numbers. We have zinc that's by itself, so it's zinc in its elemental form, so we know that the oxidation number is 0. So for nitrate here, the oxygen has a rule that it's always -2. There's 3 of them, so that gives me a total of -6. So what plus -6 gives me a -1 charge? Well, it has to be a +5. So nitrogen in the context of nitrate is +5. Now zinc here is a monoatomic ion, and of course it would be paired with something else. We've just kind of removed it out. So there might be some chloride in solution. There might be some other things that are kind of floating around that aren't part of the chemistry. There might be some sodium here, right? So there may be other ions that are in solution, but this is really the focus of our redox process, of our oxidation reduction process. So the charge is the oxidation state for that zinc, so this is a +2. And then for our nitrogen and our 4 hydrogens here, this is the ammonium cation, then our hydrogen is +1. There's 4 of them, and so 4 times my +1 is +4, so what +4 gives me a +1? Well, that must be a -3 for my nitrogen. Okay, so we have assigned oxidation numbers, and now we have to figure out what's happening. Well, if I look at kind of the main features here, my zinc is going from zinc with no charge to zinc with a 2+. So let's do our oxidation step here. So zinc to zinc 2+. Okay. All right, so let's balance this thing. When we're completing and balancing the half reaction, kind of going back to our steps here, it says we need to balance all the elements but oxygen and hydrogen. So there's no oxygen and hydrogen here, and I have 1 zinc on either side. So far, so good. So now I go to my next step, which is to balance any oxygens by adding waters. Again, no oxygens, so no waters need to be added. The third step then is balance any hydrogens by adding H+. It's in an acidic environment after all, so we can add as much H+ as we want. It's hanging out in solution, but we don't need to do that in this case because there's no hydrogens. And so our last step is to balance the charges by adding electrons, or if we have to, then we'll multiply the entire half reaction by a specific factor should we need to balance things out. So in this case, I have a charge of 0 on this side, a 2+ on this side, so I need to add 2 electrons. Now that felt like a very lengthy process to do kind of the same looking half reaction that we've done in the past, but that's the process. We're practicing the process here, and it'll be a little more complicated in our reduction step. So what's being oxidized is my zinc. Let's go to the reduction step. All right, if we're going to the reduction, then we need to say, well, what's going on here? It looks like my nitrogen is going from a +5 to a -3. So it must be reduced, right? My number goes down. So I'm going to keep the entire species here that it gives me. And it goes to the entire species here that it gives me. So my nitrogen's changing, and if you look at this, this is not a balanced chemical equation, right? It's just giving you ions in solution that are doing stuff, and you need to kind of balance it out. You're going to combine things together and balance it all out. So let's do this for our reduction. So our oxidation is our zinc. Our reduction is our nitrogen, based on those assigned oxidative states, assigned oxidation numbers. So now let's go back to our steps. So we need to balance all the elements but oxygen and hydrogen. So that would just be our nitrogen in this case. I have one on each side, so I'm good to go. I don't need to do anything there. Now I need to balance oxygens by adding waters to the side that needs them. So I have 3 oxygens on this side, so I need to add 3 waters to this side. And I can add, again, as much water as I want to in this case because these are aqueous solutions. So this is taking place in an aqueous or aqueous environment. So we have water all over the place. We're surrounded by water, and so we can use this to balance out our chemical process here. Okay, so now that I have my oxygens balanced out, I need to balance my hydrogens by adding H+. So now I have 4 hydrogens here, 6 hydrogens here. That must mean I need to add 10 hydrogens to this side. And again, I can add as much of the acid as I want as well because we're in an acidic environment. We're balancing this redox reaction in an acidic environment. Okay, so now I have the same number and type of element on each side. Now I need to balance out the charges by adding electrons or kind of figuring out what that looks like. So what is my net charge here? Well, I have 10 plus 1s. So here's a +10. And I have a -1 because of my nitrate. So my net charge on this side is overall a net +9. You with me so far? Now on this side, I have +1, right? And that's the only charge I have on that side. So this whole side has a net +1 charge. So in order for these charges to be the same, how many electrons do I need to add? And I'm going to have to add them to this side because it's the more positive side. How many electrons do I have to add in order to get the charges to balance out? Well, I need to add 8 electrons in order to do that. Okay, so now I have my zinc here with 2 electrons, and then this is my balanced reduction half reaction, taking into account the oxidation or the oxygen and the hydrogen, and then the balance of the charges here. So now the biggest thing is when I put these back together, because that's going to be sort of the take-home message here, when we throw them back together, now what happens? Well, I have 8 electrons that I'm gaining here. Reduction is gain, but I'm only losing 2 electrons. So what do you think we're going to have to do with this half reaction? Well, we need these electrons to look the same. So in order to do that, I'm going to have to multiply this whole thing by 4. So now, in my chemical process, I have 4 zincs going to 4 zinc 2 pluses plus 8 electrons. And I'm going to add to that my reduction step. And we know that we can add chemical reactions together. We've done this in a number of different contexts. You can do it in thermodynamic contexts. You can do it in kinetic contexts when you're adding together multiple reactions. And now we add everything that's on the reactant side. We add everything that's on the product side. And then we can kind of combine things together and simplify what we have. Okay, so let's do that. Here's my 4 zinc, my 8 electrons, my 10 H pluses, my nitrate, gives me 4 zinc, 8 electrons, my ammonium, and 3 waters. Okay, so when I look at what I have in common, this is kind of back to my original steps of these reactions. Combining and simplifying means I'm adding together those half reactions and getting rid of what we've considered in the past as spectators, or things that are in common on both sides. Well, in this case, it's the electrons, right? The electrons are the ones that are moving around. And there's nothing else that's in common on either side. So my overall reaction, make sure we have some space here, is 4 zinc, 10 hydrogens, nitrate, the zinc ions, the ammonium, and the waters. All right, so that's a lot of kind of steps to get you to this take-home message. This is your overall reaction. And to make sure that everything is balanced out, then it's a good thing to check your charges, because we want to make sure we have the same charge on each side. That's a good way to generally check these things. There's 2 checks you can do. One is, do you have the same number and type of element on each side? Because at this point it should be balanced like we've balanced chemical equations. So we have, 4 and 4, 10 and 10, 1 and 1, 3 and 3. And then now our charges, I have 10 plus 1s and a minus 1 here. So that should give me a net charge of plus 9 here. I have 4 times my plus 2 is plus 8. Plus 1 here is a plus 9 on that side as well. So we have our charges that balance, our number and type that balance, and we are now balanced in an acidic environment. Okay, so that's kind of balancing. We'll come back and do another example of this, as well as looking at these in basic environments as well. And I'll talk to you again soon.